Hello, everyone. My name is Andy. I'm an undergraduate at Harvey-Mudd College, and today I'll be presenting PLaID, which is a preference-aligned language model for targeted inorganic materials design. First, for a little bit of background, we know that generating novel materials is critical to many industries, from solar cells to batteries to carbon capture. However, although there are between 10 to the 10 to 10 to the 12 potential materials, the known number of materials is a much smaller percentage. Therefore, the promise of generative models is that they should be able to tap into this vast amount of chemical space, which currently our known materials are not able to access. Something that we've noticed in recent years is that actually ML for materials has been getting much better at a pretty rapid rate. So we see that a few years ago with things like CDVAE, we're at roughly between like 1 to 2% stability rate, whereas recently with talks like all-atom diffusion transformer, we're getting that number up to around 14%. We also see this trend reflected in terms of predictive models. So we also see that on the MapBench discovery benchmark, we also see that over the past few years, these numbers are getting much, much better, and we're almost close to DFT level accuracy in terms of these pseudo-potential models. That kind of leads me to believe that, driven in large part by more powerful computation and larger scale data sets, we claim that the Cambrian explosion of material science is coming. And specifically, in a world with more data, more compute, and better verification signals, then the question becomes, how do we best leverage scale or leverage computation and scale? And our solution to this is the bitter lesson. So what Sutton argues here is that as data and computational power grow, the two methods that scale best with computation are learning as well as search. And a great example of this is large language models, which is one of the things that we base our work off of, whereby they removed a lot of inductive biases, threw a lot of data at the model, and now they're miraculously good enough to write my homework and things like that. However, kind of moving in towards more specifically talking about learning and search in terms of material science, the first thing we like to talk about is naive crystal coding. So our work is really based off of one of the works by Groover et al., so some folks at Meta and NYU. And here they show that leveraging the bitter lesson, large-scale language models like Llama 2 are effective materials generators as long as you fine-tune them on crystal structures as text. However, one thing that this work is really missing is that crystals actually follow these inherent symmetries. So we actually know that crystals fall into one of 230 unique space groups, and these space groups are defined by the set of rotations, reflections, inversions, and translations on a crystal's unit cell. However, what's more interesting is that these symmetries aren't merely a mathematical construct, but rather that symmetries encode function. So one example of this is piezoelectricity, where this is a property where materials generate electric voltage under mechanical stress. And this is actually only present in materials that lack inversion symmetry. So that kind of then leads to the question of, okay, well, we know this, but how do we encode these symmetries into something that the model can learn from? And a lot of previous approaches have done some things that are quite complicated. So for example, Crystal Former here, they modeled the joint probability distribution of unit cells. We also see things like Y-Former, which do a special structure-based tokenization that includes space group information as well as Wyckoff sites, as well as FlowMem, which includes things like equivariance to model these rotational symmetries. However, what we contend is that rather than encoding symmetries in things that are really complicated, rather we can leverage the fact of scale and data itself to make encodings really easy. And the way that we do this is that starting with this crystal structure here on the left, we're able to use this asymmetric unit cell, so what's shaded in green here, and we're actually able to encode this in a string representation, which we show here on the right. And what this string representation does is that it's a more compact as well as data-rich representation, whereby just having these 3 atoms here, we're able to generate this 16-site atom. The other important part of learning here is that we actually find that language itself is really unique because it's flexible for multiple different tasks. So whereas for other types of methods, you might have to use a different model to encode different things or do a different training pipeline entirely, what we see here is that language makes it so that a singular model can easily train across multiple tasks, from unconditional generation to conditional generation to things like infilling. So that's now we have basically a relatively strong learned base model. And then the second part of this problem then becomes in terms of search. More specifically, the question becomes, how can we search the space of generations more effectively? And that kind of brings us to our second main contribution here. So this is, I think, a really great visualization to understand some of the intuition behind what we're doing. So we start off with the base model distribution here on the left. And the goal here is to generate crystal structures in this area. So this is basically energy above the hull. So we want to generate materials that are stable. Where our intuition for our paper is that we have this base model distribution. How can we elicit the model so that we actually push our learned distribution to be more towards this goal distribution? And that's kind of the key intuition behind what we're doing here. And that leads us to the solution, which is direct preference optimization. This is something inspired by the works in natural language processing. But the key idea here is that this algorithm helps guide our search space towards desirable structures. This is kind of seen in this loss function here, where on the left term, we're seeing that we're basically increasing the log probability of preferred samples. And the right term is merely just decreasing the log probability of dispreferred samples. And in the context of material science, what this means is essentially we want to form preference pairs where the good samples are stable structures and the bad samples are the unstable structures. And by forming these into pairs, we're now basically using the model's own generations to teach the model what data is good and what data is not good. And that's where PLaID comes in, which is our model here. And for a little bit of our pipeline, what this looks like is we start with a pre-trained Llama model. We then do our Wyckoff-based fine-tuning. So this is kind of the learning aspect which we talked about in terms of learning and search. And then from this fine-tuned base model, we generate or sample 10,000 crystal structures. Then we use an M3GNAT machine learning interatomic potential model to do this relaxation. And as we stated before, as these machine learning interatomic potential models are getting better, then our method also will scale with that as well. Then finally, we perform this DPO-based fine-tuning to reach our final base model, PLaID. And PLaID is able to, as we mentioned before, do all these different things from unconditional to conditional to infilling. Then here to talk a little bit about some experiments here, we train on the MP20 dataset. What we find is that, obviously as we're spotlight up here, our results are pretty good. But what's more important than just that is that we find that learning and search themselves actually compound. And what's really interesting here is that we see that although the base model of PLaID here is relatively competitive with the other methods, we see that both learning and search independently are able to improve model performance. And more importantly, these are independent axes where as you combine them, they actually compound. The final thing I want to mention here is that we see that the Wyckoff encoding itself also allows us to generate more symmetric base structures. So kind of looking at the P1, which is our least symmetric space group, we see that the base model has a much lower percentage of the base model has a much higher percentage of these low symmetry structures. But to conclude, if there's kind of one key takeaway from our work, I think it's that many of the talks today discussed how basically how can we build better data sets and build towards like the ImageNet moment of material science. And while I personally totally agree that these things are super important, I think the other key question that we should be asking is that in a domain where we do have generators and verifiers that are both getting better, how can we better utilize these advances to build a data and RL flywheel to kind of push us towards chemically useful foundational models? So really focusing on this flywheel aspect here. And yeah, that's about it. Thank you so much. Check out our paper here on the left, and I have my collaborators, Rohan and Larry, here as well. Perfect.